I added them all, so you should be good to go.
Manage slides. We're trying to put Jim's slides up.
We have the note well we've got to go through first. So there's the presentation that's the agenda and note well. And then Jim's after that. Tamara's second and Theo's third.
Okay, we have share slides.
Perfect. All right. Well, you know what we can do to save time? How about I run through this and then we'll hop over to Jim. Welcome, everyone. We're here for IETF 121, the Global Access to the Internet for All research group of the IRTF. Thanks so much for joining us in the room there or remotely. We apologize we weren't able to travel, but we have one speaker there in the room, which is exciting. So we'll do sort of pandemic remote hybrid in-person running of GAIA today. So if you could click to the next slide, Curtis. And note the session's being recorded so that everyone's aware. It's required in the IETF for us to run through the note well. This is just a reminder of IETF policies in effect on various topics, patents, codes of conduct, other relevant aspects of IETF. As a reminder, by participating in the IETF, you agree to follow the IETF processes and policies. If you're aware that any IETF contribution is covered by patents or patent applications that are owned or controlled by you or your sponsor, you must disclose that fact or not participate in the discussion. As a participant in or attendee to any IETF activity, you acknowledge that written, audio, video, and photographic records of meetings may be made public. Personal information that you provide to IETF will be handled in accordance with the IETF privacy statement. As a participant or attendee, you agree to work respectfully, and this is very important, with other participants. Please contact the Ombuds team if you have any questions or concerns about this. Information in the documents listed below and other IETF BCPs are relevant to your activity at IETF and IRTF, and just take note of that as well. Talk to working group or RG chairs or ADs if you have questions. Next slide. There's one more note well slide. And note really well, during the meetings, including virtual meetings and mailing lists, they're intended for professional collaboration and networking as defined in the IETF guidelines for conduct, the IETF anti-harassment policy, and the IETF anti-harassment procedures. If you've got any concerns about observed behavior, please talk to the Ombuds team. The folks at the registration desk can help you if you don't know who that is or how to do that. The IETF strives to create and maintain an environment in which people of many different backgrounds and identities are treated with dignity, decency, and respect. Those who participate in the IETF are expected to behave according to professional standards and demonstrate appropriate workplace behavior. IETF participants must not engage in harassment while at IETF meetings, virtual meetings, social events, or on mailing lists. Harassment is unwelcome, hostile, or intimidating behavior, and particular speech or behavior that is aggressive or intimidates. If you believe you've been harassed, notice that someone else is being harassed, or have any other concerns, you're encouraged to raise your concern in confidence with one of the ombuds persons. Okay, so this is really important. Please take note. Next slide, please. And we're, meeting tips. You can take note of this as well. You're all doing this if you're participating remotely, but just note that Meet Echo data is here. And for remote participants, please make sure your audio and video are off unless you're chairing or presenting during a session. And use of a headset is strongly recommended. That just helps with the audio quality. Next slide, please. Thanks, Curtis. Other resources for IETF 121 Dublin are here. Next slide. And onward to our fabulous speakers. Jim Cowie's up first. From the Internet History Initiative. Jim is with the Berkman Klein Center for Internet Society at Harvard University. Jim, over to you, and let's, if you can pull up Jim's slides, that'd be great, Curtis. Thank you. And sorry, I should have said Jane Coffin and Curtis Harmroll were the co-chairs. Curtis, do you want to do a quick intro?
Yeah, hi, welcome everyone. Obviously difficult time with us being West Coast here. It's 1:30 in the morning, so you'll see me a little low energy. But really excited to have everyone there, especially those folks who came in person to Dublin. I'm Curtis, co-chair here with Jane. I'm an associate professor of computer science at the University of Washington, and GAIA is a long-running working group here at the IETF focused on internet access for folks that are on the outside of the internet right now. Jane, would you like to say something about yourself?
Thank you, everyone. My name is Jane. I'm a longtime person involved in the interwebs and telecom and other related topics, working now on a project to connect schools. Otherwise, as Curtis said, part of the IRTF, IETF research group GAIA for quite some time, and just honored to be able to see you all today. And thanks to Curtis, who will help with the slides because I don't have that access, but over to you and Jim, Curtis. I'm here to help as needed. And we'll help moderate the queue, everyone. Jim, over to you.
All right, I take the floor. Can you hear me well? No, is this not live? Table not live.
The audio is pretty wonky. I think you'd have to.
Yeah, maybe talking to the mic.
Yep.
Like the big one, yeah.
Take this one. How about that's live?
Much
Yes.
better.
Right, good. And we'll not use this one. All right. I wonder if my clicker works. There is a clicker here on the table.
Can help you move the slides. That clicker is tricky.
It's just decorative. Okay. Cool. So thank you everybody for coming online or in person. I'm Jim Cowie. As already mentioned, I am a research fellow this year at the Berkman Klein Center, where I'm putting together this project on the Internet History Initiative, which I'll describe a little bit here and maybe show how I think it aligns to some of the goals of GAIA. My background is not as a historian or, in fact, as an academic. I'm a technologist. I was one of the founders at Renesas back in 2000, and we did internet measurement for a long time, and then eventually got acquired by another company, which got acquired by another company, which lost all of our data. Basically, if you go to that, the acquirer's acquirer today, which is a large, let's say they're a second-tier cloud provider with more lawyers than engineers. There's no trace of the data that we accumulated over the years. So everything we presented on, all the papers we put out, all the presentations we ever made at global forums, all the data behind those is gone. And that inspired me to think a little bit carefully about what we might be able to do as a community to not do that quite so frequently. It didn't just happen to me, it actually happens as a recurring pattern. I'm not a historian. A better way to think about it would be perhaps as a librarian. I always wanted to be a librarian. And at the Berkman Center and also at the Harvard Law School's Library Innovation Lab, I'm connected to some really good people who are specialists in the archival of digital content and the preservation of history. So next slide. So I apologize, you will get exactly one slide of Simondon because since I'm an honorary academic, I have to honor the patron saint of technology. A philosopher of technology, he was interesting because he denied that there was a difference between technical reality and human reality, that was not supposed to be a natural alienation. He famously looked at an oil pipeline coming across the Algerian desert and noticed that it passed right by the people who lived there. There was no intersection between the advancement of that amazing transport technology and their natural lives. And so he said this quote, which I love, which is that transforming all the conditions of human life and augmenting the exchange of causality between what man produces and what he is, true technical progress might be considered as implying human progress if it has a network structure whose mesh is human reality. So this is 1959, but he's anticipating something which has come to be, I think, which is that the internet allows all human technologies to proceed in a mesh, and it modifies the very way that people pursue science or pursue connectivity amongst themselves. Okay, that's the only philosophy slide here, I promise. So next slide. The purpose of the initiative is to take a good hard look at how this all came to be. And it really is just the blink of an eye in terms of human history. The whole thing fits nicely within not only my lifetime, but my adult lifetime. The fact that we could get from a 4-node network to the network that we know is an amazing path. And then the job of recording and inspecting and curating history is to figure out whether that was the best path. Are there alternative paths? What were the key decision points where this could have gone better for all of us? And then to look forward, are there sensitive places where we could apply pressure or creativity and take it down another path? So next slide. This is my favorite path not taken. This really gets deep into the history, right? This is a moment in the summer of 1992 when the IAB, which had just renamed the A to architecture, decided that they were going to solve the problem of address space consumption and routing table explosion, which was manifest by that point. And in 1991, they realized that the total number of internet connected hosts was doubling every 12 months. By the time they got to 92, it was doubling every 3 months. And they realized they were in some serious trouble because of the way that they had structured the allocation of IP addresses. And so this is the very moment in time where things really get serious. People invent Mosaic. So demand is being driven. Meanwhile, there's a religious war going on between the IETF, the IAB, on the one hand, championing TCP/IP, and the old OSI, Open Standards group, standardized by ISO, which was, it was governments, it was telcos, it was big corporations, it was IBM, all working through a membership and voting system to try to laboriously work out a more intelligent networking stack that was going to be better thought out than what we've ended up with. And there was a huge religious, I keep saying religious, it was a social debate. It was a conflict of standardization theories between these two groups. And so we reached this moment in the summer of 92 where the IAB at their Kobe meeting says, we've reviewed this and we need to go ahead with CIDR because that was going to take at least a little of the addressing pressure off. We need to move ahead with what we'll call IPv7, which will be based on the connectionless network protocol that we will borrow back from OSI. OSI had built CLNP as a connectionless protocol based on IP. It was very recognizably the same kind of protocol, except it had it had 20 bytes for the address field instead of 32 bits. So it would have given us IPv6 style plenty. And interestingly, because OSI was being so well regarded by some parts of the community, not this community, but the US government, NIST, the vendors were taking it very seriously. And there was already CLNP code deployed in routers. The NSFnet had been capable of routing traffic in CLNP for a year. And we could have just gone dual stack with this. And then there was actually a product, there's a RFC 1347 TUBA, which is TCP plus UDP over big addresses, which just would have done that. And we would have dual stacked for a year, 2 or 3. There were fewer than 1 million hosts in the world at that point. There were probably fewer than 1,000 routers. And we could have done it. And we could have been, we could have never had the 30-year still imperfect transition to IPv6. So I'm sorry to belabor one slide, but that to me is a moment. And when you go back and look at the history that has converged around the IETF, there's very little memory that this was even a possibility. Within a couple of years after the IAB's membership or board had to be replaced to get behind the decision to stick with TCP/IP, most of that debate was forgotten. And it moved forward, set in stone. You know, this is how history is made. So next slide. And it leads us to this, right? So as a result of not getting the address space we needed, we had this continuous shortage. We were all running out. It became a zero-sum game of everybody fighting everybody to get IPv4 addresses. And you get these frictional effects so that in developing economies everywhere else, it's not easy to start new things, or not as easy as it could be. So as a result, the first mover advantage of specifically the US tech industry just compounded on itself. Success breeds success. Multiplicative growth compounds. And so here we are today. If you watched Jeff Houston's Ripe Talk, you hear this very pessimistic but internally consistent picture of a world where the applications people have run away from the IETF, that they have built out an edge full of content that is one hop from every user that they care to serve. And that makes routing irrelevant. And it's just feeding caches. That's all the internet is good for, is feeding caches at the edge. And there's a pessimistic view there that people who come onto the internet now, because it's now a client-server internet, don't need IP addresses. Because all of us out here who consume content are not really internet participants in first class. We're not providers, we're just consumers. So that's the game over. You know, drop the mic, that's the end of this mode. So the question is, can we play again? And that's the fundamental question of where the history goes. So next slide. We can play again. So what I've set up is just a simple meeting place. It's the Internet History Initiative, a place where we will connect and discuss over ways of preserving the data and the history that describes the paths that we've taken so that we can figure out how to argue for better outcomes in the future. Next slide. So if the internet is worth anything at the level that we are working on here at IETF, it's that it retains that permissionless end-to-end innovation ability, right? This is the key feature of what we want to preserve, is the generative properties of the internet. It's a game you can play over and over. If you don't like the way it has come out this time, you just go out and build another one on top. Now, the problem is that coordinating around that means that we all have to find each other and tell the same stories. We have to tell creative stories about why the internet could be better than it is, or how it could have been better than it was. And that's the motivation for building this repository. So next slide. Okay, so now, you know, enough. We're 15 minutes in. We have to get to the actual work to be performed. So here's kind of the work plan that I'm working my way through here after a couple months at the center. We want to go out and engage the institutional holders of the content and the data sets. Some of them are at the right there, and none of these folks have endorsed me, although I've talked, I think, with all of them. They hold the data, and in many cases, they hold the only copy of this data. And by data, I'll show you what I mean in a second. But it's all the history of internet measurement that records the growth of how we got where we are. All of these organizations are amazing, and they all have potential constraints on how they can preserve and showcase that data. All sorts of constraints. What we want to do is to first bring them into conversation with each other on this specific topic. Second, bring some research librarians to the table. Research librarians are quite good at thinking through how to deal with preservation and curation under tight resource constraints. We want to make copies of everything. We want to replicate that so that it's safe. We want to build some curation around it so that researchers can access the content from all of these repositories together as some sort of data lake strategy. And then finally, once we've all done that, we'll take it out on the road, as it were. We'll tell stories with scientists and find media storytellers and journalists and everybody else who might be able to help us tell these stories better. And in particular, we want to explain why the internet is such a benefit to the newly connected, the promise of what it brings to societies as it arrives. Next slide. So as I've already kind of hinted, history is very complex, and it has many different lenses through which you could construct the records that historians will use. As I said, I'm not a historian. I don't have that training. A librarian role is more appropriate because what we'll do is collect, and you don't disclaim all responsibility or judgment there. You do have to decide what to collect, and that imposes a view on the collection. But by and large, we want to collect whatever is available in terms of the history of measurement. So we'll start with the recording of routing tables going back. We'll go through performance measurements and so forth on up the stack. The fact that a lot of people have already done oral cultures, studies, ethnographies, they've done interviews of the old folks. The fact that there's so much available right here in the data tracker, going back all the way to the historical period I described, all the web pages of all the projects anybody's ever worked on. All of this stuff ultimately needs to be preserved together to give the context, because the real historians may not show up even in our lifetimes who can understand what this meant, right? Because it takes the passage of time, probably at least decades, to get the kind of perspective on what this meant and to get out of the way of the people who are still around polluting the arguments with their preferences, to figure out how to build frameworks to describe what has happened to all of us in the last 50 years. Okay, so next slide. This is just a scatter plot. It's not a scatter plot, it's just a scatter splat of a lot of the projects that have some of the data that I want to pull in. And it's very ecumenical, I want everything, right? We'll start with BGP routing, we'll work our way all the way up to unexpected places. We realize that the Internet Archive, every time they scrape a page, has metadata in the scrape from what IP addresses were actually being used by the servers that returned the content. This never shows up in the Internet Archive front end, but it's there in the metadata. You can use it to reconstruct some early DNS resolutions going back into the 90s. I have one here that's boxed because I want to show you something interesting. This is Pinger. I don't know if anybody here ever used the Pinger data. This was Les Cottrell's project at the Stanford Linear Accelerator Center. Next slide. Les figured out early on that he could get money to monitor the performance of the internet. Before there were internet studies, there was less. And so he was trying to figure out how to make the internet fit for purpose to move content around for physics projects between high energy physics centers. And so he had a very simple project. He wrote it himself. He would send out 10 ICMP packets, and then he'd see what he got back in what order. That was it. And so one line at a time, over years and years, he built up this continuous data set of how the internet looked from 1997 onward. And it ran all the way up until May of this year. Les was interesting because while he was getting funding from US Department of Energy to monitor the performance to high energy physics institutions, he was actually picking out global South universities and places in sub-Saharan Africa and Pakistan and everywhere else where he could measure to on a continuous basis. And we thought this data set was dead. I went there this summer as part of the effort to try to find out how to recover it, and found out the data was down, it was gone. And I got back in touch with Stanford IT. We managed to get some of it remounted, and I'm making a copy of it now. So it's gone from extinct to endangered, right? It's like finding one member of a species left in a jungle to recover the data set. Next slide. This is the kind of work that he was doing early on to try to figure out whether there were correlations between packet loss and jitter and implied bandwidth into particular countries and the International Development Index. He wanted to figure out, even though he, like me, was not a social scientist, whether you could grasp at some of these initial connections between development and internet performance. Again, using this wonderful continuous data set. So this is a preliminary success story. I'm happy to say that we will be able to have a copy of this entire repository for the world to look at and do research on. So next slide. A little bit hard to see, but this is the RIPE Atlas network. Each hex here this is a log scale. So the darkest red have about 250 Atlas probes in them, each cell. And the faintest ones have one. And it's a beautiful measurement network, but as all measurement networks are prone to it, it has some inherent biases based on where the probes are located. And to their credit, RIPE Atlas does a wonderful job trying to get this balanced, trying to get more probes into the places that they need, specifically into the ASs that they need in order to have a good, a comprehensive coverage of what's going on. But it's an illustration of the fact that since all measurement systems have bias, and since all of our measurement systems so far have bias towards the wealthy countries of North America and Europe, that deficit or that bias compounds over time because we can't go back. The internet changes every day. You can't go back and measure the internet of yesterday today because it's a different place. So once these opportunities are lost, that loss compounds, and we don't have the long time series. We're going to need to do the best science. Next slide. I think we're getting towards the end here. Very quickly, it's an illustration of some of the kinds of data that we can do. We have the historical data in RIPE Atlas for example, how all the probes get to Google Public DNS. So you can go back over 5 years, day by day, and find out how everybody got to Google Public DNS. And if you map it out into watersheds, you see two things. One, there is some it's hard because there aren't enough probes in the interesting places you'd really like the answers to. But two, there are some interesting long hauls. For example, all of the Russian-speaking world is dragged to Finland, all the way out to Vladivostok. Things like that are interesting because they reveal how the big public platform folks think about harder to reach parts of the world and where they're going to serve them from and what choices they're going to make in terms of investment. And next slide. Finally, and I really should just wrap this, one of my themes here, one of the reasons that I struck out for Harvard was to meet scientists who were outside our community. I think we've spent a long time as internet research people doing internet research on the internet, using the internet data so we can talk about the internet. And instead, we have social scientists, most obviously economists, who really want to understand the features of developing economies, for example. And they're well aware of the fact that as the internet has come ashore, it has changed everything, and the economy has changed the internet. And to study those things together takes a career scientist with perspective and tools. So this is, I guess, the final point of the Internet History Initiative is to take these repositories and generate long-term metrics that are clean enough that we can get into co-authorship with good scientists like these, who will take a look at how the internet affects and is affected by conditions in emerging economies, including everything from employment and income inequality to conflict studies to public health. Everything is on the table. Next, and I think final slide. This is it. So in conversation with you, the ways I think you can help me selfishly. One, the only way I find out about endangered data sets is when people tell me about them. It's unlikely, and in the extreme, I'm going to stumble over them by myself. So if your organization has measurement data from the olden days or is continuing to collect measurement data, if you can figure out a strategy for saving it, this is the time to have that conversation, because by the time the budget cut comes or your manager's gone or your leadership changes, it's probably too late. You have to it's like estate planning, which we don't like to think about, but without careful planning in advance, data is basically default dead. I would love pointers to other papers by other researchers that you respect, who you think would do a good job with these data sets. We're always looking for new connections. And finally, and this is truly finally, I would like to find people who have stories of local communities as the internet came into their lives, because these oral histories become guideposts that historians will use to align to our data and say, aha, okay, the reason that this shift in provider interconnection is important is because it correlates rather neatly with the following effect, which was seen on the ground by the people who experienced it, which is in the end the only thing that matters. Final slide. That's it. All right. Well, thank you very much. I appreciate your attention, and I can take questions. So thank you very much.
Thank you, Jim. Does anyone have any questions? I think we have a queue.
Nalini in the queue. I'm going to join the queue myself.
Nalini, you're up. Curtis after Nalini.
Yeah, thanks. Nalini Elkins, Inside Products. I'm trying to wrap my head around a little bit what you're doing. I've been involved in the IETF fairly long time, and I'm well aware of the Kobe debacle, and it's the IETF is a complex and also human organization, and there's a lot of different things that have happened. I'm a little unsure. I guess your goal is to be really talking about the if I can be reductive, is like the impact of the internet on the global south. Was that a adequate statement?
It's a little reductive, but in a good way. Yes, I want to talk about the impact of the internet on civilization broadly, but I think most of the usefulness here will be on the global south. But it's also a two-way street, right? It's not that I think the internet community often assumes an approach which is kind of a sort of technological determinism, where the internet arrives and things get better, and that's manifestly not the case. It's there's a subtle interplay between the way that employment opportunities change, the way that gender relations change, the way that everything changes as the internet weaves its way in and gradually becomes available to some but not all people. Some of that we will be able to figure out, I hope, by providing these data sets. The earlier part about the IETF and its internal culture, I think, is just a way of signposting that the culture of the IETF and the culture of all the other institutions that helped push the internet out into the world is itself going to be a really interesting thing to study alongside this.
Yeah, maybe I should just take this offline, because this is a very long conversation, because I've certainly been involved in quite a few bloody battles, which especially encryption. I was also in the Peace Corps, so I'm well aware of the conversation. I mean, we had many conversations about what happens when, in fact, you do something like you have an oral language and you move it into a written language. I mean, and the impact on culture. I guess it's the scope is very, very broad, it seems like, and good luck. Yeah. Oh, yeah. Thanks.
Okay. Thanks, Nalini. We have Curtis up next in the queue. So Curtis, and after Curtis, Theo.
Yeah, so I'm really interested about the participation bit here. There's a lot of data out there, and there's a lot of people who built this infrastructure. Is it really just like all of that's relevant, or is there some kind of filter that we should be applying beforehand?
Right. So just not to drive myself crazy, I am starting with the infrastructure measurement. So that is interdomain routing and ping and trace route, and the basic recording of things like zone files and where the content lived. Ultimately, trying to get to a model of taking slices of experience. So if you were a Chinese academic researcher in the year 2004, how would you have reached Google at that moment in time? Those are sort of slice of the internet questions that we could look at specifically. Yeah, it's an open question, because I don't want to prejudge what we want to collect. the pack rat in me says, find everything that is endangered and make sure that it does not disappear, then apply curation as a community, and then move on to the society questions, kind of in that order, because if we mess up the preservation part, if we accidentally lose something that is a real key part of the puzzle, we won't be able to go back and pick it up later.
Thank you, Jim. And note for Jim that there's some great links being added to the chat. And we'd also invite you to use the GAIA mailing list as well for a call for info and data. I believe, Theo, you have a question. Go for it. Say it out loud and we'll have it recorded.
Sorry for that. Can you guys hear me now?
Yes.
Yes.
Okay, so my question was, I like the fact that you highlighted this geographic bias in the data sets you collected. But I think the biggest challenge I see right now is actually trying to close that gap. We were trying to do a study of how has connectivity evolved in East and West Africa, and going through a lot of the RIPE Atlas data, there is actually not enough data for us to actually do a study like that. We're working with RIPE to try to find ways to close the gap, but I feel like a lot of the data sets seem to have the same geographic bias. And so a lot of what we will learn will be extremely biased. And I worry about trying to make broad generalizations based on that. And I think when people talk about connectivity and probes in Africa, a lot of that essentially just means South Africa. So I think the broad question here is, do you have some tips, initiatives, or kind of active work in terms of trying to find ways to expand any of these measurement platforms?
I don't have any initiatives in particular. I support the concept, and I work with measurement teams to try to think about how to close those gaps. I guess really the only thing I can specifically do through the History Initiative is to give evidence that these are problems that if you're going to bias towards a solution, you would be towards having a solution that you could make progress on quickly, because the absence of measurement compounds over time. And whatever we figure out to start today to get more measurement into some of these places, we may not see the payoff in terms of enough consecutive longitudinal data for, until our careers are over. It'll be our children who have to figure out what that data could tell us, which is a little bit depressing. But yeah, I'm in favor of better and broader measurement, but I don't have a specific initiative to improve it.
Thank you, Theo. John, you're up next, John Clenson.
Yeah, I'm sort of in agreement with your conclusion or assumption about data collection, but I fear that there are potentially biases and misperceptions in how you're looking at the problem and how you're looking at turning points, which may influence your ability to interpret things. There's a specific example, and noting that I go back longer than even Naomi. Your analysis of the Kobe decision as a big turning point is very important in terms of how the IETF has evolved, of course. But in terms of how the network has evolved, it's worth looking at what the alternative would have been had we gone down the OSI path. A lot of the IETF objection to the OSI path at the time was based on two things, one of which was that the OSI model had not been demonstrated to work except locally. And the other is that it was dominated by national governments and their, because at that point it was not independent in most governments, in most cases, they're captive telephone carriers. And part of the OSI problem because of that was a connectivity issue with lots of national profiles which did not interoperate. and gateways in strange third-party places like the US, because it was illegal to use the profile of one country in another country and vice versa. And as a consequence, you couldn't even have in-country translation gateways. So, long story, probably useful off this conversation. But again, my concern is that you've captured a couple of interesting points, but overinterpreted them in ways which distort the way you're looking at the data and the way you're looking at conclusions.
Thank you. That's useful. Yeah, I think this is not something that I can. I'm certainly not trying to weigh in on how the internet should have gone, but just pointing out that these are turning points. There have been real historians who have gone carefully through this material. Andrew Russell wrote a really good book about standards processes through this period and looked at some of the competing issues, and some of his conclusions. It's one lens through which he sees history. Was that the relevant technical bits of the protocols may not have been compared as carefully as they could have been, given the feelings were running very high on exactly the topics you're talking about, implications of who was controlling the process on either side. So yeah, I'm not advocating for we really should have done this differently, but as an illustration of the fact that we do have to collect history carefully and then pass it off to professionals who do history, so that they can come to multiple conclusions about what this all meant. It's not going to be us, I think, as I said at the start, my role in particular, I think, is more along the lines of archivist or librarian, trying to collect what can be collected so it doesn't disappear, and then pass it off to people who may not be born yet, who will figure out what the heck this meant.
Again, no disagreement there, but if I were to interpret your first few slides and the associated comments, it would sound precisely as if you were saying, path not taken, the other one would have worked.
Thank you. Thanks both. We're going to close here so we can hop to our next speaker. Thank you so much, Jim. We really appreciate you presenting, and look forward to seeing what you can collect. There's some good information in the chat, and thanks for being a steward of the data. I think the next speaker up is Mesh++.
Oh, I put the wrong one up.
That's okay. Theo's after them. So Tamara and Danny, we're going to turn it over to you. You have 25 minutes to present. How about it?
Great. Good morning to everyone in Dublin. We're so happy to be joining you. My name is Tamara Hamden. I'm the COO at Mesh++. I am joining you all from Mexico City, so it is the wee hours of the morning here, but we'll try to keep it energetic. Danny and myself will be switching off. Next slide, please.
So, hi, I'm Danny.
Yes, go ahead, Danny.
Great. Hi, I'm Danny. I founded the company a few years ago. My background's in wireless communications. This isn't a super academic presentation. Mainly, we wanted to tell you a little bit about the work that we do, and some of these examples of connectivity that we've had. Next slide, please. Our goal as a company is to bring the internet to areas that are difficult with traditional infrastructure, whether this is a niche corner of an existing network or a very remote area. That's really our goal with our product and associated with software. The next slide has a video that we can try to play. If it doesn't work, no worries. But would it be possible to try playing the video on the next slide?
I don't think we have that functionality.
No worries. We essentially, to give a summary, we make a device that looks like this, usually has a solar panel on top, throws up on poles or rooftops, or even in trees. They'll automatically connect to each other and form large-scale mesh networks to give context to some of the rest of the presentation. And then we'll dive a little bit more into that. Next slide, or I think it might be 2 slides. We're based in Chicago and Nairobi, so I'm calling from Chicago. We make our devices here that serve the North American market, and we have actually a larger office in Nairobi where we serve East and South Africa. We're still a fairly small company, 15 to 20 people, and we are essentially built up of engineers from a lot of the major wireless companies. If you could skip 2 slides again. Here is our product, the S618. This is what really our whole offering is based off of. It is a bunch of batteries and a bunch of radios packed into a tube, essentially, that sits underneath a solar panel. We as a company started as part of research into low-loss mesh networking protocols, trying to expand the range of your standard Batman Advanced or your BMX, so that you could cover much larger spaces. And we ended up building that into this product. It's a Wi-Fi 6 device, so Wi-Fi 6 access point to the end user is essentially what it appears as. Next slide, please. It connects to a variety of different backhauls. Our average network connects to a fiber backhaul. You plug in one of them, and like any other mesh network, it extends that access over a very large area. Generally, we'll have multiple uplinks for a given network. So if we're covering a few hundred acres, we might have cellular 4G or 5G hooked into one of the nodes, and another node will be hooked into fiber Ethernet. One of the more exciting uplinks that we've been using more and more lately is Starlink, or rather, I should say, our customers or partners have been using, where we can really multiply the impacts by spreading out that connection. It's generally solar powered, but you can power it with anything you've got. One cool thing is it can power secondary electronics, and so in the field, sensors or cameras or anything that's powered over PoE will be able to use the excess solar power from this device to power those other radios. The device itself has proved to be really weather resistant and quite durable. We admittedly overbuilt it a little bit. It has a 3mm aluminum frame, and we've tested it to IP68. Just so that we could make sure this connectivity was not only resilient from a networking sense, a network that's difficult or impossible to take down because of redundancy in the uplink, but also a network that is difficult to physically take down. Next slide, please. Ultimately, our founding patents and our founding protocols boil down to a dramatically lowered loss per hop as long as you have a highly organized network. We do that through time slotting. It leads to, in a large-scale network, as long as it's relatively ordered, you have similar distance between nodes, the mesh will require around 17 times less cabling. Fewer gateways is essentially what that means there. We use multiple uplinks in these large networks to utilize all of the bandwidth available, but also make sure that there's redundant access. So the network is very difficult to take down. One cool thing is these large-scale networks start small, and you can easily add to them. It is an ad hoc network at the end of the day. And that allows the networks to grow a little bit more organically. Later on tomorrow, we'll talk a bit about some of the specific applications that we've done, but the ability to grow a network one node at a time, one mesh node, one access point, quickly put that up and be able to extend the range allows us to tackle applications a little bit differently and even empower new business models. Next slide, please. Here's a little bit on the internal of the device that I just held up. To be honest, it's mostly batteries. It's a solar-powered product. It needs to be able to survive longer-term weather patterns, and so for that, lots of lithium-ion 18650s inside this guy. But you'll see the blue polycarbonate windows on either side, which hide various antennas, Wi-Fi 2.4, 5, 6 gigahertz, LTE or 5G antennas, GPS, Bluetooth. Those are all hiding either in the polycarbonate windows or can also be hooked up to external antennas. All of those radios are modular on the inside. We have M2 and mini PCIe slots on this custom small board that we've designed so that you can plug in various radios. Some of the cool applications that people have used these for is, this is a tube with power and connectivity available on the inside. We've had folks throw Raspberry Pis, for example, inside of the device so that they could have an onboard server that they have a little bit more control of, that's a little bit more flexible than our device itself. Everything is enclosed, which makes it fairly easy to transport. It only takes a couple minutes to install, and we have made sure that it's modular for expansion in the future so that when we set something up, when there's a new Wi-Fi standard, when there's new radios or new sensors that somebody might need to install, that's something that they can do without purchasing a new device. It's something they can just easily add. On the next slide, you'll see our dashboard. We keep our management system fairly simple. Our goal with really everything we do as a company is to automate as much as we possibly can. So we will first and foremost make sure that the software will do anything it can to figure out how to get the network up. That includes figuring out whether a node needs to be a gateway or a mesh node to operate, what sort of uplink it has, how to configure that, how to prioritize that. And then once the network is online, then we have advanced configurations that a network engineer might prefer, because they might, of course, prefer to just hard code the system to operate a certain way rather than our firmware try to figure out exactly what to do. On the software, the UI side of that simplicity initiative, we have the management through a map. So you can see a heat map of the network, how many users are connected to the network graphically, the bit rate and quality of the mesh links between the nodes, and everything's color coded as well. So our goal with this is to enable somebody who is not an engineer to be able to install a network, know how it's doing, and be able to troubleshoot various issues. A lot of times we'll install networks in remote areas, or rather our partners will, and they'll be able to do that just with whoever happens to be on the ground, because in the most basic sense, you just turn on the node and it will figure out how to get online, and it will configure itself in a default way with its peers. And then we'll be able to optimize or do any other configurations that we need to do remotely if necessary. But since they're connected to the internet, there's no need to have somebody on site most of the time. Next, I will hand it over to Tamara to speak more to some of the applications that we've targeted.
Thank you, Danny. Next slide, please, Curtis. and the next one as well. So this is a community that understands the strength and the power of community networks to close the digital divide. And so I'm going to spend the next couple of slides taking us through how the product Danny just introduced us to, the S618, is extremely suitable for driving community networks. There are 5 primary reasons we've distilled for that, and they begin on the next slide. So the S618 has the ability to bridge connectivity gaps. It brings internet access to underserved or remote communities where traditional infrastructure is too costly or unreliable. The device, as Danny underscored with the Hurricane Ida example, is both sustainable and resilient. Solar-powered solutions like the S618, of course, reduce dependency on conventional power sources, which in a lot of the communities still without broadband access, that those power sources can be sporadic or unavailable at all. And so solar infrastructure is more resilient to power outages, to natural disasters, to fuel outages, and is inherently far more cost effective, of course. Next slide, please. Our devices are scalable and really easy to deploy. It's easy to start small and add nodes. And why that is useful is that there's no need for the extensive wiring or grid access. And so networks can both be very quickly deployed, but they're extremely nimble and can be scaled up or scaled down, modified to provide coverage to this area of a village as opposed to that area of the village, if not the whole village in and of itself. And these devices, given their the characteristics we've spoken about and the intuitive web tools that Danny presented, they're an affordable and self-sustaining technology that encourages local ownership and control. Communities can maintain these networks, expand and operate them independently. The idea at inception of this company was to build a device that a non-technical person, set of people could manage. And so that is really plays in quite well to the needs of community networks that don't often have network engineers within those communities. Next slide, please. Of course, they have long-term and cost-effective impact. There are minimal operational and maintenance costs for these devices, reduced need for frequent replacement of equipment. These devices are a sustainable investment that benefits communities over the long term. So now we're going to take the 5 key drivers of the product's fit for community networks and zoom out and look at the range or a range of applications for the S618. You'll see as we head into those that it's quite expansive with many applications and existing deployments that are community network adjacent and some that are less adjacent, but that share characteristics with community networks. Next slide, or perhaps 2 slides, Curtis. Yeah. Thank you. So we have a network live in Mandela Park that's outside of Umtata, South Africa. The genesis of this network was a partnership with Elitha Telecom in a USTDA or for a USTDA funded network that would bring broadband to 30,000 residents of Mandela Park. This was once an informal settlement outside of Mtata, South Africa. That is Nelson Mandela's birthplace. But over the last several decades, this formerly informal settlement has taken on a lot of permanence. Although on the utility side and on the infrastructure side, I'm still a lot lacking by way of power. For that reason, our devices, which are completely self-sustaining, can be completely solar powered. We're an ideal hardware fit. And while this network has been commercialized and expanded, its use case is similar to those for that a lot of community networks would be considering, would be dealing with, and that is like a utility constrained environment. Next slide, please. We sent a number of devices to Maui in the wake of the 2023 fires. We did this with the aim of creating fast deploy Wi-Fi networks for use of displaced residents who were staying in community shelters. And the intuitive web tools made the resulting networks manageable by non-technical community members who've since deployed those devices for community networks after this original post-disaster use case. Next slide, please. We have provided the Wi-Fi to the Mobile Education Unit for Computers for Schools Kenya. They have a mobile classroom you see pictured here. At the moment we shot this, it was in Namanga, Kenya, although it moves around. This mobile classroom travels to different Kenyan villages, providing a short-term Wi-Fi access to its residents, bridging the digital divide, allowing them to be in contact, take online classes, access telehealth, etc. Next slide, please. In 2022, in the wake of the Russian incursion of Ukraine, we sent 50 S618s to the Ukrainian Ministry of Digital Transformation. Their goal was to aid in restoring connectivity. These devices, often paired with Starlink satellite, were deployed in urban and peri-urban areas that suffered infrastructure damage. The Starlink backhaul example is one we wanted to underscore. Of course, the near ubiquity of high throughput internet access is creating a lot of opportunity for for networks to be very quickly deployed. Those high throughput connections, of course, create a single high throughput connection. Our devices very efficiently and inexpensively distribute them. And so we're a great complement to Starlink, to a Starlink kit, to Amazon Kuiper, etc. Next slide, please. The Shadowwood Mobile Home Park in Champaign, Illinois is an example of a Mesh++ partnership with the city of Champaign. This was a pandemic era deployment where the goal was to create internet access for student residents of this mobile home park, and to allow them to participate in remote education. This network was made live in an afternoon. Next slide, please, Curtis.
Sorry, give me a moment.
In 2020, we partnered with the city of New Orleans to provide free Wi-Fi networks in 2 local parks frequented by residents of the underserved neighborhood of Triangle City. This is the network that Danny referenced, having withstood Hurricane Ida. In August of 2021, at which point, on the occasion of that natural disaster, the city reached out for the network's expansion. Next slide, please.
Just a 2-minute warning.
Okay. Thank you. Does that include questions, Jane?
You have 10 to 12 minutes for questions after you're finished with the presentation.
Okay. Great. So I'll just breeze through these next couple. We partnered with a Belgian IT company to establish a 60-node network bringing Wi-Fi to downtown Goma. This is a DRC city at the base of a volcano you see pictured here. Next slide, please. Just jumping ahead, so the Chicago Parks District and the City of Chicago reached out for our support, providing free Wi-Fi at nearly a dozen parks and schools across Chicago. The city had at this point been exploring various solutions for connectivity at its parks, and selected Mesh++ for its ease and expediency of deployment, the resiliency of the nodes, and this was extremely supportive in creating connectivity for residents of the areas surrounding these parks during COVID. Next slide, please. Just an example to underscore the device's ability to create short-term networks, as was the case in Garrido Municipality that hosted a 2-week technology and cultural event. Next slide, please. Next 2 slides, actually. We thank you for being here. Want to emphasize that we have a network design tool. You see the URL for it here on your screen. You can create a polygon overlay of any area you are interested in, and it will help design a network for you, indicating roughly how many nodes you would need to create coverage there, how many gateways. Next slide, please. Well, 2 slides. That brings us to the end of the presentation. We thank you so much. This is how to reach us if you have any needs and or would like to learn more. Next slide.
Thank you, Tamara and Danny. We have Vesna who, Vesna, if you could join the queue electronically. We have Robert up, Robert Richter, and then Vesna after Robert. And if you could keep your questions short and your answers short, we can add more people in to ask you questions. So Robert, over to you.
So thank you. I'd be interested in, you had said that you are often pairing with Starlink, and do your devices actually power Starlink? Because as far as I know, Starlink also provides a router. So how does that work?
It can power a Starlink temporarily. It has enough peak power output, but over the long term, we would have an increased risk of downtime because of how much power the Starlink terminals use. For all of these kind of higher powered electronics, we have a tool to simulate what the risk of downtime would be based on solar data that we have over the last couple decades. But yeah, in general, not sustainably.
Okay, thank you.
Hi, it's Vesna. I have a question. Do you have some devices that are not new but repurposed or secondhand, or that have been returned and they can be used for the non-commercial or not-for-profit projects, or for even poorer countries? Thank you.
We do have some of our older Wi-Fi 5 model, if that would be suitable. I don't think we have a lot of extra 618s floating around, but if you were interested in the same concept of the automated mesh with Wi-Fi 5, we can reconnect after the call.
Thank you.
Thank you, everyone. Does anyone have, do we have any other questions for the team at Mesh Plus Plus, who's working with a lot of community networks and communities around the planet? And you have both Tamara and Danny here on the call, on the GAIA call here. So if you have other questions, just pop them in the chat. And Tamara and Danny, thank you so much. We appreciate you joining us today. And we'll be moving over to Theo for your presentation.
Thanks for having us.
Thank you, Danny. Thank you, Tamara. Appreciate you getting up early. Theo, over to submarine cables.
All right, thank you for inviting me to give this talk. This has been a very interesting year to kind of be around traveling in Africa. So I spent most of this year traveling. And one of the things that has made this year exciting and interesting is cable cuts. So I was in Nigeria right around the time of the West Africa cable cut in Ghana. I spent most of my time in Kigali, and we've had a cable cut with submarine cable cut. We've also had some terrestrial cable cuts that have affected us. So it's been one of these years where cable cuts happen. It leads to kind of service disruption in whatever region gets impacted. But this has been a year where we've just had many of these cable cuts. And one of the big things that we've had discussions about is how has the introduction of caches, the introduction of rules that require localization of services, how has those impacted availability? So several countries, including Rwanda, have rules that specify government services have to be local within the country, and yet many of these services continue to get impacted by cable cuts. So one of the things that got us thinking is we focus a lot on let's make content local. Once content is local, a lot of things will change. So there were a couple of things that got us thinking how much of the content is local now? And given the amount of content that's local, why are a lot of these cable cuts leading to significant outages and unavailability of online services? So that's a lot of what this talk is going to be about, is looking at different data sources to try to explain some of the hidden dependencies that allow these cable cuts to have magnified impact. Next slide, please. So one of the earlier cable cuts that happened, as I said, was in West Africa. And I think one of the things that, if you pay attention, you realize is when the cable cut happened, it impacted many countries. It led to significant loss of revenue. But one thing that I think most people don't realize is that uh, a lot of your kind of basic utilities you pay for via mobile services. When these cuts happen, you're unable to pay for your basic utilities. So think about this. You need to top up for electricity, you need to top up for mobile connectivity. I think water you don't need to top up for, but gas for cooking, you have to sometimes top up for that. When there is one of these outages that last multiple days, you're unable to pay for electricity. When you're unable to pay for electricity, it disappears. So there were lots of instances and kind of radio conversations, eventually articles coming out of Nigeria and Ghana about how many of these basic utilities, people were unable to access them, and that actually magnified the impact of the submarine cable cut. So submarine cable cut happened. You could not access any web services. You could not pay for any of these utilities, and a lot of things basically just came to a halt. Uh, and when it happened also on the east side, something similar occurred. And when we get impacted here in Rwanda by any of these cable cuts, something similar also occurs. So these cuts, obviously they lead to service unavailability, but then they lead to broader disruptions in terms of lack of utilities. They also bring down many organizations, businesses. For example, many of the ports in West Africa could not accept cargo because they could not access the manifest, which was digital tie. So there's a much bigger impact than just I cannot access Netflix. It's basically much of my essential services are unaccessible when any of these cuts occur. Next slide, please. What we set out to do here was characterize the connectivity performance at different locations, look at the outages, look through the effectiveness of alternatives. So there has been a widespread uh, push to use Starlink in the face of many of these outages. So one of our goals is to try to characterize Starlink usage and deployment characteristics. So, what performance do we get here versus in the US? Does performance of Starlink uh, is it comparable to terrestrial? Is it better than terrestrial in different parts of Africa? And then there's the other thing where looking ahead, there are a lot of efforts to try to create more terrestrial connectivity in Africa. Google announced a project. These will be multi-year projects, but can we start to create more probes, deploy more probes that will allow us to assess how richer terrestrial connectivity improves um, availability and reliability. And the last part is trying to design more protocols or design additions atop BGP to deal with many of these outages, to reduce the time between when an outage happens and when resolution occurs. Right now, a lot of these outages basically take a significant amount of time to resolve. Physically, it takes forever to resolve, but logically, there are ways where we can speed up the rerouting that needs to occur. So, what I'll focus on in this talk is more how do we characterize these outages and what are some important things that we need to start thinking about when we think about resilience in different parts of Africa. Next slide, please. Much of the data sets we use in this analysis are from two sources. One is Cloudflare has Radar, where there's a significant amount of historical data that we can go to. So this is another source of historical data. The other one is actually Apnic. There's a typo here, but the other one is Apnic, which has a lot of DNS analysis. And since then, we've also been looking at RIPE Atlas data to better characterize layer 3 connectivity. So to characterize IXPs, to characterize BGP paths. But this talk will focus on the analysis we did with the Cloudflare data and the AppNic DNS data. Next slide, please. So starting with the Cloudflare data, one of the things that we try to do is look at outages across the world. Uh, Turns out outages are not unique to Africa. There are loads of outages that happen, and many of these outages actually do have impact on end user. So this graph is looking at the outages that have impact on users from Cloudflare's perspective. So outage that has an impact on user means lack of connectivity. Many of these outages that do occur do not have an impact on end users because of the redundancy that already exists in many parts of the world. Um, so each of these bars is a different continent. The leftmost one is Africa, and the big thing to highlight here is that these cable cuts have impact on have a much higher impact here than they do elsewhere. I think another thing to notice is that there is also significant amount of government directed outages that occur here as well as in Asia. But a lot of what we focus on is the fact that there is a lot of this outages that are caused by the cable cuts themselves, and that it happens actually happens everywhere, but the impact here is much, much higher. Whenever these cuts happen, they impact many countries, and there are a significant number of these cuts that a significant number of different countries have been disrupted over time. Next slide, please. One of the very interesting things about these cable cuts is, unlike terrestrial cable cuts, where you can find a crew, send the crew to go fix it, and you can expect a turnaround within days. For much of the subsea cables, when a cut happens, it takes significantly longer to actually fix the cable cut itself. It takes longer because you need to actually hire a ship. The ship has to make its way over. And one of the things that once you start talking to operators, you realize is that you can hire a ship, the ship can make its way over, but you also need to get approvals from many government agencies. And this is non-trivial. And so it takes significant amount of time. So a cable cut by itself will take months to fix. Some of the cuts that happened earlier this year were only just fixed last week. So the physical cut itself takes a large amount of time to resolve. Alternatives to that is trying to reroute your traffic over other cables that exist. This also takes a long amount of time. When we look at a lot of the post hoc analysis of many of the cuts, like the government of Ghana released a document about the cut that happened in West Africa. And there's a huge amount of effort that has to go in terms of coordinating between different providers to get extra bandwidth, uh, get extra kind of uh, fiber capacity from different providers, and then only after you've gotten much of this capacity and these agreements can you start rerouting the traffic. And a lot of these agreements, given sufficient traffic forecasting, many of these agreements can be made beforehand, but many of these agreements right now are being made kind of on demand, and this inflates the time for resolution for kind of rerouting around a cable cut. So the figure here shows the time it takes for different types of outages to get resolved. Where resolved here just means traffic and services are available again. So when the outage happens, how long does it take before services are available? And there are several different comparison points here. There is kind of all outages in Africa, Europe, South America, and then there are the cable cuts themselves. And the big thing that we see here is that in general, outages in Africa, which is the blue line, take longer to resolve. There are the logistical issues here take a bit longer than elsewhere, but the cable cuts themselves also take longer than general averages. And this is because of the kind of multi-party engagement that's required to resolve them. One of the things is kind of at the very tail. It looks like the cable cuts and all outages in Africa take roughly the same amount of time at the kind of tail end. But one of the things we observe is that these are actually maintenance of these cables. They're technically not cuts, but maintenance events. So events or cuts, maintenance related to any of these submarine cables take much longer to resolve because of a lot of logistical issues around them. And one of the things we're trying to do now is to create traffic forecasting mechanisms that can be used to help speed up much of this capacity planning, much of this multi-party stakeholder agreements that need to be made. But the key thing from this is that uh, these cuts, unlike other outages, take significantly longer to try to resolve. And there's an opportunity here to try to close this gap by providing tools that create a lot of the kind of capacity planning that is currently required. So that's one of the things that we're also looking at right now. Next slide, please. One minor thing I want to talk about. I said there is kind of a lot of these multi-party stakeholder agreements that need to go in. One of the many things that doesn't get discussed is these cuts have a prolonged impact on the region. So as I said, the physical cut itself takes many months to fix. So the solution is to reroute traffic. When you start to reroute traffic, you actually see a degradation in performance in other regions. So capacity is fixed. When more traffic goes on fixed capacity, there is some degradation. And if you start to look at things from the BGP layer, you actually see shifts in IP address spaces. So there is kind of a pronounced impact in terms of what quality people can expect during this kind of period of rerouting. But there's also like a shock when you start to look at the kind of control center of the internet, and a lot of the articles that have come out are kind of governments trying to talk about how do we prioritize traffic during this periods of degradation. And I think one of the issues here is that many of these countries start to rely on each other, and a lot of the prioritization, a lot of the differential service are often discussed within the context of one country. And we need to start thinking about how can we help inform or create signaling mechanisms to allow for multi party or multi kind of country cooperation when you're trying to deal with this constrained resource during this periods when there is kind of extreme rerouting happening within different regions. So this is something where I would spend much time on, but I just wanted to point out that while we are able to recover availability within a couple of days, there is like significant degradation that lasts for sometimes months. And during those degradation periods, managed services suffer, and there's a question of how do we try to determine maybe some kind of prioritization scheme or some kind of differential quality scheme that can help alleviate the congestion that is occurring during these periods where a lot of traffic is getting rerouted through a small number of alternative paths. Next slide, please. So the next set of slides are essentially trying to understand why a lot of the effort that has been made to make traffic local, to make content local, while in face of much of this effort, we still see significant outage impact. And this slide is just a primer. What happens when you try to visit a web page? You visit a web page, you have to first do a DNS request. Once you get the DNS information, you get the IP address, you can now route to a data center or an edge location that might have the content that you need. One thing that I think many of us often forget is that while the edge location has much of the content that you need. To log in, you still need to go to a data center. So for many of these services that require you to log in, that require dynamic content, you often still need to go to a data center. And when you start looking at Africa as a whole, there are very, very few data centers here. I believe Meta currently does not have a data center here. And there's a heavy reliance on WhatsApp and a lot of Meta services. So once you're logged in, you can kind of work with some of the edge services. But if an outage occurs and you need to go to a data center for any of these, then it becomes unavailable. It doesn't matter how many edge services exist. It doesn't matter how much local the cache content is. If you can't get to a data center for some dynamic information, uh, then you're basically stuck. So there are a lot of dependencies that arise when you start to think about what needs to occur to actually just get a service. There's obviously content itself. Some of it is not local, uh, and we often focus on the content. But also, DNS resolution is crucial. And some of this, a large fraction of this is itself not local also. So it doesn't matter how much effort you spend as a country to localize services if there's still a heavy reliance on this external DNS resolvers. Then during these outages, you actually will have a bunch of connectivity issues. In addition to these two, there's also several complex factors at the routing layer that also add other issues that we often overlook. So I wanted to quickly go through some slides where we essentially look at data from several sources to see how much progress we've made in trying to make many of these dependencies local. So we'll essentially start off by looking at content, since that is where much of the focus has been. So next slide, please. I apologize for the presentation, but this is a graph. Oh, can we go back? Yes, thank you. This is a graph that we made earlier this year. It's some work with ISOC, joint work with ISOC, that was presented at ANRW, and it's part of a larger project to try to quantify localization of content across the world. Here, I focus just on three large economies in Africa. So looking at South Africa, looking at Kenya, and looking at Nigeria. And the kind of key thing here is we look at South Africa, and much of the effort to localize is kind of creating fruit. We see that over 70% of the content is localized, whereas when we look at the other two countries, there is significantly less localization of content. And I think you look broadly across the continent and you'll see a similar kind of pattern where there are a huge number of countries where localization still has a lot to do. So when we think about what is the impact of an outage in West Africa, well, there is, like in Nigeria and several other countries, there is huge reliance on external resources. So these cable cuts will have a larger impact there just because the content itself is less localized. We'll look at the cuts that happen in South Africa. There are some Amazon data centers in South Africa. There is a large set of caching, a large set of carrier neutral data centers also in South Africa. So when the cuts happen there, there is kind of less of an impact. And I think you see in 4 minutes, yes, in Kenya and on the east side, we have kind of half of the content localized. So there, the kind of impact is maybe not as large as the West, but there is still kind of an impact in terms of the content that you need to try to access. So next slide, please. Let's skip ahead 2 slides. So as I said earlier, there's also the kind of DNS aspect. And one of the things we observed is when we start to look across the different regions, there is a huge impact on uh, non-local resolvers. So we look at East and Central, and about half of the resolvers are non-local. Much of this is to the cloud. So essentially, while there has been a huge amount of effort to try to bring the content local, uh, with many of these countries, a lot of the government services are localized. There was a lot of complaint that people could not access these government services, and in reality, the complaints were the DNS. We were unable to access the DNS resolver to get to the government services, but kind of much of this gets conflated. So one of the things we're trying to do now is to highlight the role of DNS, but also the hidden impact of relying on cloud DNS resolvers to kind of provide something that's reliable. Is in terms this cloud DNS resolvers are making things unreliable themselves. So let's jump ahead 2 more slides. So this is probably the last kind of results analysis slide I will present. One of the things that was done by Roderick Fonteau and several interesting researchers almost a decade ago was look at the amount of localization of traffic. So how much of the traffic gets routed locally. Uh, I've just shown that we still rely heavily on remote DNS. We still rely heavily on uh, remote content. But when we actually start looking at one of these large providers, and these large providers have caches everywhere in the world and has a lot of caches even in Africa, we notice that while there are caches here, a lot of the traffic still goes to Europe. So this provider specifically has a large number of caches spread out across Africa, and yet because of routing issues, a lot of content still goes to the cache locations in Africa, in Europe. So right now, more than half of it still ends up going to Europe, and much of this can potentially be tied back to DNS. Much of this can also be tied back to routing and peering. Some of this can be tied back to content placement itself, but there are a large number of these factors where placing caches does not by itself make things local. Placing caches does not eliminate unavailability when we cannot access data centers themselves. So there are a large number of other dependencies that we need to start thinking about beyond just focused on caches themselves. So I know I'm almost out of time, so we'll skip 2 slides to what will be my last slide. So we are looking at these cable cuts. We're on the ground right now, trying to collect more data. We're trying to create more analysis that tries to identify some of these hidden dependencies, and kind of more long term. As I said, we are looking at Starlink deployments and trying to characterize the performance and how that scales. And hopefully, as we start to deploy more of these probes, we can have an infrastructure that will help us assess the evolution or the massive amounts of evolution that we see coming within the several years ahead. We are looking for other partners in other kind of regions of Africa to work with in terms of deploying probes, but also in terms of working with other people to kind of do more characterization studies of different aspects of the network. With that, I will stop and leave for questions.
Thank you, Theo. That was excellent. Do we have any questions? I may have one or two, but I want to, of course, defer to everyone else in the room and online. So anyone in the queue? Robert, you're up.
So thank you very much. Few probably already said it, or I just missed it. How do you actually define an outage, or how do you know that you're currently looking at an outage?
So the outage analysis right now is based on Cloudflare data. So Cloudflare has a team that looks at kind of their network telemetry and annotates the different outage events that they observe. And these outage events are essentially inability of customers to access their resources. There is a similar project out of Georgia Tech that we're also looking at their data right now. But most of the outage analysis are a set of groups that monitor connectivity via either probes or via actual customers. And then an outage is detected when whole countries, I think in this case of Cloudflare, it's either whole countries or whole ISPs, ASNs are able to access their services. And then they go and also manually investigate. And for some of these, since I've been kind of working more locally now, there is conversations with the local operators to confirm it. I think for many of the ones that are actually annotated on the Cloudflare Reader, it is confirmed with discussions.
I see. Thank you very much.
Theo, more of a follow-up to Robert's question. Not, will you see outages that Cloudflare doesn't report?
Right now, since we're using their data set, no. This is one of the reasons why we're now also incorporating the IOTA data set, which will allow us to see a different set of outages. But once again, this is based on their vantage point. We're in discussions with Catchpoint to get access to some of their data. But I think a fundamental limitation here is for each of these entities that we're engaging with, they have a specific set of vantage points, and that limits what set of outages we can detect. I think the one good thing about some of these outages is that when the cable cut happens, it impacts a region, not just one country. So,
Unless you're landlocked twice like Kyrgyzstan, right? Because you'd be super
yeah,
downstream.
yeah,
Right.
but so
Yeah.
Rwanda is landlocked, and
True.
so whenever anything happens in um, Kenya, we always get impacted. I am part of the Kenya Network Operators Group, and whenever someone in Kenya is like, "Is connectivity slow?" and a bunch of people organize and they figure out which provider it is,
Exactly.
I start using the network, and I'm like, "Ah, yeah, it was only a matter of time." So.
Long live the network operator groups, the NOGs.
Yes, yes, long live them. So I think with the cable cuts themselves, they will impact not just one country. They'll have a larger kind of disaster zone. So combinations of various data sources will allow us to detect that. When we go for terrestrial cuts, that becomes much harder
Different,
because those
much
are
harder.
hyper localized.
Yeah, that's a really great. Thank you for making that observation, Theo. That's really important. The terrestrial cuts are a completely different issue, and I've seen terrestrial cuts in places where someone had a backhoe and didn't know what the local the city plan was, and this was in
Yeah,
Armenia
that's
where they
actually what
dug
we're
up
trying
the
to get.
network.
Yeah, that's what we're trying to get to there is the terrestrial, and that's a lot harder than the subsea cables. There's a lot of documentation about where they are, what their capacity is for the terrestrial. There isn't as much. There is an interesting project out of Mozilla Open Fiber, but there are some gaps in that. So I think if anyone has access to these amazing terrestrial fiber, we are always willing to work with them.
Okay, and shake it out on the Gaia list too. That'd be great to start a
Yes.
conversation starter. Meaning, here and there. We have Tara in the queue. Tara, over to you for a question for Theo.
Thank you, Tara STA. So I was wondering, also I think in vein of the last question, is there also perhaps a difference between sort of unintentional or accidental outages and maybe more intentional blackouts, or is it similar to the terrestrial case? I'm thinking in terms of specifically transnational effects.
Yeah, so that's a very good question. I think one of the events that happened in Kenya uh, a couple of months ago, people initially thought it was a cable cut. It ended up being kind of a shutdown of a sort. We haven't tried to look at the differences. I think there is going to be some differences kind of in the characteristics of these shutdowns, but we haven't looked at them yet. Like they actually are part of the graph where we look at what fraction are cable cuts, what fraction are government shutdowns. So we see that they are significant in Africa and Asia, but we haven't looked at what are the performance implications um, of these cuts. And one of the things why I believe it will be different is so when the cable cut occurs, there is a best effort to try to reroute all traffic. Some of these shutdown events, uh, because of how they are set up, there isn't a best effort to reroute all traffic. Some of these events are because of school exams, and in those cases, there is no effort to reroute traffic. In some of the other cases, there might be some effort, but in some of the cases, like the school exams, there's a large amount of traffic where there is no effort, intentionally no effort to reroute it. So that's one thing we haven't done. There is a team out of Georgia Tech that has looked broadly at the differences between different types of shutdowns, and we're hoping to kind of work with some of their data when we try to look at the differences that we see here.
Thank you. Thank you for the work.
Thank you, Theo. I don't see any other requests for the floor. I am typing something in the chat for Vesna or for Miriam Kuna to see if there's any similar projects that are going on in Europe. Maybe RIPE can be a source of partnership, Theo. They do some great work.
We've been talking with Emil at RIPE.
Bravo. He's lovely.
Yeah,
Okay.
so we getting some probes from them during my next trip, and we're trying to work with them on trying to find ways to do more of a Starlink deployment here also. So they've been very responsive.
Cool. Very cool. Okay. Well, then shout out to the RARs, the NOGs, the PIFs, and the everyone else, and of course the ACMs of the planet who are doing great work. Well, I think that if there are any other questions for Jim, I think you're in the room. I'm checking to see if we have. No, we don't have Tamara and Danny. They had to go for other meetings. But if there are any other questions for Jim or Theo, we have about 10 more minutes. Speak now or give yourselves back 10 more minutes for your coffee break. All right. Anything, Curtis, from your side before we close?
Nothing here. Thanks to all the speakers. This was a very nice set of talks that I greatly enjoyed. And yeah, everybody out there in Dublin, go get a cookie.
And please use the GAIA list for asking folks questions and or collecting more data. We would love to see that list more active. Okay. Well, thanks so much, everyone. Good luck with the rest of your meetings there in Dublin. And to those that join remotely, thank you very much. And we appreciate your time. So thanks a lot.